just remember what the question is, okay? You have this 40, 75, 85 triangle, right? Which when you divide everything through by your common factor, which is, common factor? 5, okay? You can see it's an 8, 15, 17 Pythagorean triad, one of my favorites, it's very nice. 5, 12, 13, also nice, but 3, 4, 5, it's too mainstream, you know? So this is why people often don't spot it like, you know, immediately, okay? So there's my right angle. Now you can see, you have to situate this semicircle. You want to get the maximum area, which really means the maximum radius for your semicircle, and you've got to use one of the sides to form part of the diameter, okay? Or all of the diameter, by the way. So you can obviously see this is not the biggest semicircle that I can fit, because I have a longer side I can choose over here. But to find the area of this, the method I'm going to use will help you work out the areas that you're getting, okay? So I've labeled a little bit. This here, which I've put with a dot, is the center of the semicircle, which is not the same as the center of AC, right? Because if it were, the circle would come out here, it would go outside the triangle, yeah? So since it's the center of the circle, I'm going to call it O. Right? Now what we really want to work out is the dimensions, this radius, right? Like this distance here, if I can work out that radius, then I've got the area in the bag. So let's just call that radius R for radius, okay? Now it's 40, 75, 85, okay? So this must be my 75 and this must be my 85, okay? Now, my shortest side here is 40, but rather than like have lots of confusing information on there, I'm just going to add on the remainder of this side, AO. What is AO? If AC is 40 and OC is R, this is going to be the difference, is it not? 40 take R. Is that all right? Okay. So what can I use to work this out? I don't have much to grapple with here. In order to work this out, I've got to get a relationship between these two. Okay? So this is the big clue, right? I'm going to put an extra construction in here on top of the semicircle. I'm going to put in this construction. Okay? Now I'll call this point, I'll call it P for point. Okay? Now it's on the circumference, and critically, it's where it hits AB, right? The semicircle intersects, it's tangent to AB, it hits just once, because if it doesn't hit at all, then I can make a bigger semicircle, and if it hits twice, I've gone outside. So I have to hit once, right? Now, have a look at this. This triangle I've made up here, AOP, you can almost even see it. What kind of triangle is it? It's a special triangle, right? I've drawn my diagram well enough that you can see it's a right angle. Now, you don't need to just rely on the awesomeness of my diagram to know it's a right angle. What piece of information do you know that tells you it's a right angle? Very good. This is a radius. OP is a radius. AB is a tangent. And as we established a couple lessons ago, the tangent is perpendicular to the radius of the point of contact. So I have a right angle there. Right angle here, right angle here. So you tell me, what's the relationship between triangle AOP and our original triangle ABC? What's the relationship? They're clearly similar, aren't they? They both have a right angle. And in fact, this angle in the corner, OAP, is common to both triangles. It's in the little triangle, and of course it's in the big triangle, right? So these two are similar to each other. Okay? So what I want lengths, don't I? Okay. So which sides can I compare one to another? Well, the easiest one to compare is that this side here, AO, right? In my little triangle, AO is the hypotenuse, is it not? It's the longer side, it's opposite the right angle. What side does that correspond to in the big one? It's AB, right? So I can compare, I can say the ratio between this hypotenuse and the other hypotenuse ought to be equal to, now, you can choose what kind of side would you choose to, what pair of sides would you choose to compare to get you some useful information? AP. What's AP? Answer? Don't know. You don't have enough information. Like it's less than 85, clearly, but you don't know how much less. You have nothing about that. OP, on the other hand, you know exactly what it's equal to, right? What's it equal to? It's the radius. It's the same as this radius, right? So therefore, 40 minus r is the hypotenuse of the small triangle. R is another side of a small triangle. What does it correspond to? Does it correspond to the longer non-hypotenuse or the shorter non-hypotenuse? How would you be able to tell? How can we actually work out? What features do you use to tell whether it's this one or this one? Any takers?
Right angle.
So I've got the right angle, right? I've noticed that this is the side opposite the right angle in the small triangle, and this is the side opposite the right angle in the big triangle. Eric, do you want to make a suggestion?
Yeah, R is opposite A, like angle A.
Good. Let me be a little more fine on that. OP, that side, which happens to equal R, it's opposite the marked angle, right? So therefore, what it must correspond to in the small triangle must be the side opposite this angle in the big triangle. Does that make sense? Do you see why, I actually didn't do it in this case, but why we make a big deal about like corresponding sides and angles and all that kind of thing? You match these up, so you can match these up and not mark it up. This is going to be 75. Okay? Do you need me to show you what to do from there? You can get R from this, can't you? Let's just quickly rehearse it together. What am I going to do? I'm going to multiply across, right? Oh, gee, 75 by 40. 75 by 40, 3,000? 3,000 minus 75R, right? 85R. Now what?
Take the 70R to the...
I'll take this over the other side, okay? So before I do that, I might as well divide through by some number that'll make this easy for me, like say 5. That'll make this 600, that'll make this 15, that'll make this 17. A little bit better, isn't it? Okay. Add that 15 over here, that's gonna be 32. Am I right? Okay. What can I do here? Well, you could just go that. That's going to be a bit of a funny number. What's it equal to? What do you get? I'm thinking I'm getting 18.75. Can you verify that for me?
Yes.
Yep. There you go. There's a radius. Now, it is clearly not the biggest radius of the biggest semicircle I can fit, but it is one, and you can see the way that I did it. Okay? I wonder if you can use this tool to try and work out what is the biggest semicircle. The smallest semicircle, the smallest biggest semicircle, is on this side. And the reason why is because that's the smallest side. That side is 40, right? So clearly, if I'm building it off of the 75 side, I can get something bigger. And this is what I get, right? So I compare R, right, which is opposite the common angle, with 40, because that's also opposite the common angle, just in the big one, right? R on 40 is 75 minus R, that's the hypotenuse, over 85, which is the other hypotenuse. Yeah? Okay. Then I cancel out a factor of 5, multiply across, and that's my radius. Okay? So that's a significant improvement on 18.75, as you can see. But logic does tell us that using the very longest side will get us better results. Okay? So how do we actually work out like all of the distances here? Again, there's a single construction that you need that will help you. Every time I'm taking advantage of this fact that the tangent is perpendicular to the radius, right? Here I have two choices, right? I'm tangent to both sides. Do you see that? Tangent to both sides. So actually, in some senses, I could use either one. To keep the numbers smaller, I'm going to go over there, okay? So I must be at right angles to that there, which creates a right angle triangle in the top. This is R. Yep. I've already got this side over here being 75, okay? But to do some comparisons, right, I need to know like two lengths in this triangle, just like I got two lengths, R and 75 minus R, right? So I have to choose here. If this is R, I've got to be able to work out this side or this side. Which do you think would be easier?
R.
Do you think the hypotenuse would be easier to work out, or that vertical side? The vertical side is easier, but how am I going to do it? Because I know that the whole thing is 40, right? But I don't know what the pieces are. Or do I? There's some extra information on here that will help you, right? Remember we said the tangent is perpendicular to the radius. So this is a badly drawn. I tried my best. It's quite hard to do this accurately. If you had a compass, you'll obviously do a much better job. But there's a right angle happening down here, right? And that's also the radius. 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 See that? which means this little part in here in the small right angle triangle I made, of course, is 40 take R, right? 40 take R. Okay, so I've got 40 going along here. So now I can do my comparison, okay? In the small triangle R, that's the longer non-hypotenuse side. So it should be 75. Yep. I compare that to the vertical one, that's 40 take R on the shorter non-hypotenuse side, which is 40. Right? Are you satisfied with that statement? Let's get rid of our factor of 5. That'll become 15. That'll become 8. Yep. Yep. So now let's see, let's cross multiply. So I'm going to get 8R over here. What am I going to get on the right hand side? 15 by 40? 600 minus 15R. So I just need to add, I guess, 23. Right? So therefore, and this is how I could so easily tell if you had the right answer or not. 23 is prime. So you can't simplify this fraction down any further. It happens to be approximately, if I'm right, 26.09. Let me just double check. Yeah, which is why I had to laugh when someone by measurement found 26, right? You're never gonna measure that 0.09 with your instruments unless you have an enormous diagram, right? 26.09. Okay? And look at this. This is just as simple in terms of arithmetic as any of the other semicircles we made, but it's harder to see. It requires some real work in this triangle. Okay?